Hi there, I'm Professor Rad, and this is Precalc video 224, logarithmic notation and evaluation. So in this video, we're going to talk about some of the notation that's used with logarithmic functions, and then we'll start to dabble with evaluating some logarithmic expressions. To help us out, I've relisted our properties of logarithmic functions over here on the side. We developed these properties from the fact that logarithmic and exponential functions are inverses. So we essentially applied inverse principles to exponential properties to get these logarithmic properties. Now we also defined what a logarithm was. So remember, if you have log base a of x equals y, that means a to the y equals x. And there's this sort of cyclic motion to changing from one form into the other. So for example, here we would have a to the y equals x. That's how we change into exponential form. Or log base a of x equals y. So in this video, we're going to put some of those principles to use and change, get used to this notation and how one could go about evaluating a log, because it feels kind of strange. It's like when you first learn about a fourth root and you're like, fourth root of 81, how the heck do I figure that out, right? So now we have like log base 4 of 81. Well, how do we figure that out? So here's our notation. This notation that we're going to look at is, you know how sometimes mathematicians take some shortcuts. So like if you have the cubed root, you need to put that little 3 there for the cubed root. But sometimes you'll just see a root without anything written there, right? And if nothing is written there, you're supposed to know that it's a 2 secretly there, because the square root is used so often that mathematicians got lazy and didn't want to write it. So there are 2 logarithms that are most commonly used. And so they get a little sloppy and they have an implied base, just like the square root has an implied index of 2. So that's this notation up here. The first one is called the common log, or the common logarithm. And this notation looks like a log without a base, just like the square root looks like a radical without an index. So when that happens, the implied index is not 2, it's 10. It's because we work in base 10, we have 10 digits. So log base 10 became a common log to be used. The other one is called the natural log. This is a lowercase ln, so for log naturel. So ln is for our natural log, and that means log base e of x. So remember that e is our natural exponential function, that's Euler's constant. So if we have a base of e, we shorten that by writing ln of x. So because these 2 are used most frequently, I suppose I should underline natural log as well. So because these 2 are used most frequently, your calculator most likely has a button for the common log as well as for the natural log. All right, so with that notation under our belts, let's go ahead and work through some examples. So for this first example, we want to write each exponential equation as a logarithmic equation. So that means we're going to be going from the exponential form into the logarithmic form. So we start with the base, go to the other side, say equals, and then is the exponent. As a check, remember your logarithm should equal your exponent. So at the end of it, you should have whatever, like for this first one, the exponent is x. So we should have a logarithm equal to x. So I'm going to start with the 2.1. That's the base of my logarithm. So we have log base 2.1. Go to the other side. That's the argument. So log base 2.1 of 5 is equal to the exponent, is equal to x. There we go. That's how we rewrite that expression. So same thing here. We have a log with a base of e. So log base e. Here's our argument w. And that's going to equal the exponent of 2. Now, as we're becoming accustomed to using this notation, writing out log base e is okay. But over time, you want to be more comfortable with writing this as the natural log of w is equal to 2. So you want to become comfortable with this log base e and natural log conversion. Now for these next examples, we're going to be going in the opposite direction. We're going to be starting out with a logarithmic equation and writing it as something exponential. But notice that the cyclic motion is still the same, right? So the base of the logarithm will be the same as the base of the exponential expression. So for this first one, x is the base of my logarithm, so that will be the base of my exponential expression. So I'm going to start out by writing x. Then a logarithm equals the exponent, so 1 is the exponent, and it's going to equal the argument of 7. Now on this one here, we don't have a base written out explicitly, which means it's a base of 10. So the implied base here is 10. So if you want to, you could rewrite that as log base 10 of 5 equals m. And now we can use our cyclic motion. So we get 10 to the m equals 5. So 10 to the m equals 5. There we go. So that's how we can change between exponential into logarithmic or logarithmic form into exponential. So now let's apply this technique of changing the form to work through some evaluation. And again, just like it took you a while to kind of make sense of radicals when you were first learning about them, right? Exponents, those make sense, it's repeated multiplication, but undoing that repeated multiplication is like really strange, right? So radicals were kind of harder to grasp and took a while to master. The same thing's going to feel true for logarithms because we're essentially undoing the base of an exponential expression so that we can bring that exponent down to the land of the living instead of living up in the clouds. So take your time, write out logarithmic expressions as equations, and that will help you to evaluate them. So let's do some examples of doing just that. For this example, we're going to evaluate 5 different logarithmic expressions. So if you want to pause and copy those down now, you can. Otherwise, we can just work through them all together. So for this first one, we have log base 2 of 8. So to evaluate a logarithmic expression, I'm going to turn it into an equation and have that equal something. So I'm going to use x, but you can use your favorite letter. Then we're going to rewrite this in exponential form. So we have 2 to the x equals 8. So 2 to the x equals 8. From here, you can either figure out the answer just by looking at it. So in this case, I'm going to know this is a 3. But if you also want to write this as an exponential equation that we can solve where we have the same base on both sides, you can do that too. So for example, if I were to take that route, I would then say, okay, well, I know that 8 is the same as 2 cubed. So now I have an exponential equation with the same base on both sides. So that means the exponents must be equal. So x is 3. X is the name that we gave to this logarithm. So log, let me write it over here. Leave a giant smudge on the board. That's always fun. So log base 2 of 8 is equal to 3. There we go. So we'll do a similar approach for this one here. So we have log base 3 of 1/9 is equal to, this time I'll use y. Why not? So I'm going to rewrite this in exponential form. 3 to the y equals 1/9. So we have 3 to the y is 1/9. Now, just as we did before, our goal was to get the same base on either side. So we can do this here as well. I know that 9 is the same as 3 squared, so that's good news. But I don't have 9, I have the reciprocal of 9. Remember that negative exponents mean reciprocals. So since 9 is 3 squared, 1/9 is 3 to the minus 2. So I can write this as 3 to the y equals 3 to the minus 2. So from here, we now know that y has to equal -2. And so we can say log base 3 of 1/9 is equal to -2. There we go. So we just evaluated 2 logarithmic, these are definite logarithmic expressions. They're definite because they have just numbers involved. These next three, you'll notice, are not so definite because we have some variables that are in play. So when we evaluate these expressions, we're going to assume that we don't have any issues with our variables. In other words, we're going to assume that the base is not 1 and it's a non-negative value. So in this case, I'm going to just do the same thing and see where we go. So I'm going to set this equal to x and have a to the x equals 1. Now, here's the question. A number to what power is going to give me 1? The answer there is 0, right? Because anything to the 0 power will give you 1. So in this case, that means that x is going to have to equal 0. You could also think of 1 as a to the 0 to get that exponential equation. So a to the x equals a to the 0, therefore x has to equal 0. What this means is that if you have a log with any base and you take the log of 1, you're going to get 0. Well, this corresponds to our property of the x-intercept. When the argument of the logarithmic function is 1 and you evaluate it, you end up getting 0. So this property of the x-intercept is exactly the same thing that we're saying here when we go to evaluate this logarithm. So if I have log base 7 of 1, 0. Log base pi of 1, 0. So it doesn't matter. We'll take a similar approach for this one here. So again, I'm going to set it equal to something. And I'm going to say a to the x equals a. Now, when you don't have an exponent written on a value, it's implied that the exponent is 1. So in this case, we have x is going to equal 1. In other words, the base and the base are undoing each other here, and we just get 1 out of it. So we have log base a of a is equal to 1. We actually also have this on our list of properties for logarithms. So this is this point here. Log base a of a, so if a is the argument of the function, then 1 is the y value. So if you're taking log base a of a, you're always going to get 1. So the natural log of e, 1. Common log of 10, 1. Log base 5 of 5, 1. Okay, so it doesn't matter. These essentially are kind of like they're undoing each other. And lastly, let's take a look at log base a of a to the r. Now remember, logarithms undo bases of exponential expressions. So this one should equal r, because if this logarithm undoes that base, we should be left with the exponent. So that's our hypothesis. We're going to get r out of this. So let's check it out. If we rewrite it, we get a to the x equals a to the r. Yeah, now we have a nice exponential equation. So we can set the exponents equal to each other and get x equals r. So indeed, a logarithm does undo the base of an exponential expression. So log base a of a to the r is equal just to r. This, by the way, is going to be instrumental to us when we go to solve more complicated exponential equations. So hold on to your hat because we're going to need this here. So in fact, what we've been doing for these last 3 examples is we're developing some deeper properties for logarithms. We already had these 2, but they were stated in terms of a graphical property and a graphical representation. So now we have them stated as algebraic properties as well. We also have this new one too. This is going to be a super helpful algebraic property. So we're going to continue exploring properties, but not in this video. That's what we'll do in the next one. So in the next video, we will examine more properties of logarithmic functions and delve a little bit deeper and see what other kind of fun properties we can get to. So I hope you found this video on evaluating logarithms and logarithmic notation helpful. And I hope you have a magnificent day. I'll see you next time.